Welcome to my first video in my new Thermodynamics series. In this introduction, I'll be focusing on the essential basics behind thermodynamics, as well as a quick review of basic physics. So to start off here, what exactly is thermodynamics? A book definition of thermodynamics is simply the science or the study of energy, as well as its relation to heat. And what exactly is energy? Well, that's simply the ability to cause change. And that could specifically be physical changes in an environment. So, for example, let's say you're trying to move a box across a floor, then obviously you're required to apply energy in order to move the box. Where moving it is, of course, the change that you're making, and you're applying this as a force, which, of course, by using the right amount of force, you will be able to push the box a certain distance. And that's where we can derive the term for work, which is simply that force that you're applying to the box times the distance which you have moved the box, and that is measured in the units of energy, such as joules, which I'll go ahead and discuss further in the video. And now, what is heat? Well, intuitively, it is of course the quality of something being hot, but I also like to think of heat as high energy or temperature. So for example, let's say we have a pot that's filled with room temperature water and is placed over a hot stove. Then of course here the heat from the stove will start flowing into that water. And the stove here is of course hot at high temperature, and the water relative to this stove is at lower temperature since it's colder. And so this heat is increasing the energy of the water molecules, causing them to speed up and bump into each other, as well as bounce off of the walls of the pot, which is essentially related to an increase in friction. And so that's, of course, basically heat visualized. And so now a little bit more behind the term thermodynamics. The word thermi is Greek for heat, and the word dynamis means power. So from this you can tell how the word thermodynamics was derived. So now we move on to the concept of energy transformations. And for example, this is related to power generation and refrigeration. And so in power generation, of course, first we typically begin with some kind of mechanical form of energy, which is usually driven by a form of heat energy input. And we convert this mechanical energy into electrical energy through the use of rotating shafts and an electric motor. And then, of course, lastly, we turn this electrical energy into power, which is delivered to our homes. Next up, we have the iconic conservation of energy principle, which of course states from physics that energy cannot be created or destroyed, and it can only be transferred from one form to another. So as we saw in those last few examples, energy was not being created or destroyed, and was rather only being transferred from one form to another, such as heat energy into mechanical energy. And another important thing to keep in mind is that the total amount of energy remains constant or unchanged. And now as a more elaborate example of this, let's say we have a rock at the edge of a cliff. Then this rock at this height is said to have a max amount of potential energy and is at 0 kinetic energy since it's not moving yet. But if you were to push the rock off the cliff, then that potential energy will quickly convert to kinetic energy as it falls to the ground due to gravity. And so, in other words, we will have less potential energy and more kinetic energy until the rock hits the ground and comes to a complete stop, reducing the kinetic energy back down to 0, and of course releasing some of that energy as heat and sound. And now, since energy is conserved, the conservation of energy principle tells us that considering only potential and kinetic energy, the total energy at the beginning, E1, is equal to the total energy at the end, E2, which for this case is equivalent to potential energy 1 plus kinetic energy 1 is equal to potential energy 2 plus kinetic energy 2. Again, showing how energy remains constant. So now moving on to one of the most fundamental principles of thermodynamics and just about any other science is the first law of thermodynamics, which basically emphasizes that energy is a thermodynamic property, and it is also simply a restatement of the conservation of energy principle. And with this, we also have another fundamental principle of all of science, which is the second law of thermodynamics. And this states that energy has both quality and quantity. And it also states that processes occur towards less quality over time, which can be related to an increase in entropy, also known as disorder, where things become less useful. And as I like to point out, this law is basically to blame for things not being perfect in everyday life. But I mean, it's just something that we have to work with, especially as engineers. And now from this, I'll go ahead and draw out another fundamental principle, which is simply that energy flows from high energy to low energy. And so what exactly does this mean? Well, for instance, let's say we have a cup of coffee that is left on a table, and the coffee itself is, of course, hot, as it has just come out of the coffee pot and is at 80 degrees Celsius, and the surroundings are at room temperature of roughly 25 degrees Celsius. Then, of course, here we expect the energy to flow from this high, hot area to the lower energy, colder area, which is the surroundings. And so as this heat or high energy flows into the surroundings, of course, the coffee is going to lose that energy, cooling it down over a given amount of time. And this process is called heat transfer, as we saw in the hot water example. And this process, this exchange of energy, will occur until both objects are at thermal equilibrium, which basically means that they have achieved the same equal temperature, where no more heat transfer can occur. And so basically, energy always flows from a hot area to a cold area. And now moving on to the more physical side of thermodynamics. Here we have the concept of a force. And of course, from physics, we know that a force F is equal to the product of an object's mass and its acceleration. And the units for this in SI are newtons and pound force in English units. And we know that 1 Newton is equal to, well, looking at the expression above, the SI units for mass can be kilograms and acceleration meters per second squared, as in gravity. And so 1 Newton is equal to 1 kilogram meter per second squared, just like so. And then in English units, 1 pound force is equivalent to roughly 32.1 174 pound mass, feet per second squared. So those are our basic units for force. And next we have weight, which is more specifically a force due to gravity. And it's good to note that this is different from mass, since there tends to be common misconceptions between the two. And so what this force by gravity means is basically the gravitational force that is applied to a body. And so how is weight defined? Well, it is defined by the expression W equals m times g, which is mass times acceleration due to gravity. So here you can see the similarities between the definition of a force, F equals ma, and weight, W equals mg, which hopefully helps you see how weight is actually like a force, as it is the product of mass and acceleration. And now, just to be clear here, how is weight different from mass again? Well, the mass of an object tends to remain the same regardless of the object's location, while weight, on the other hand, changes depending on the location, specifically due to the location's gravity. So, for example, let's say we have a person who weighs 150 pounds here on Earth, where gravity is roughly equal to 32.2 feet per second squared. But now on Mars, however, that person, of course, is going to weigh lower, since the gravitational force on Mars is lower compared to Earth, with an acceleration of about 12.2 feet per second squared. So continuing on with the physics concepts, taking a closer look at work. Work is essentially a form of energy, and like I mentioned previously, it is defined as the product of force and distance. And the standard SI unit for this is joules, and 1 joule is equivalent to 1 Newton meter, where you can see Newton meter comes from force times distance. And the English unit is BTU, which is short for British Thermal Unit. And 1 BTU is essentially the energy required to raise the temperature of 1 pound mass of water at roughly 68 degrees Fahrenheit by 1 degree Fahrenheit. And keep in mind that 1 Newton meter, aka 1 joule, visually means that, for example, 1 Newton is required to push a box across the floor by 1 meter. So essentially, 1 joule of energy is required to push the box 1 meter at a force of 1 Newton. Now, in addition to work, of course, we have power, which is basically the time rate of energy, which basically means how much energy is delivered over time. And the standard SI unit for power is, of course, the watt. And 1 watt is equivalent to 1 joule per second. And the English unit is horsepower. And since the derived definition of horsepower is a bit complicated, 1 horsepower is just simply equal to roughly 746 watts. So now moving on to some more distinct key concepts in thermodynamics. First of all, we have the concept of a system, which is basically any region in space that is chosen for study. And so, for example, let's say this circle is our system. Outside of this system is going to be the surrounding, which is basically the ambient mass or a region outside of a system. And now the next thing we have, particularly between the system and the surroundings, is the boundary of the system, which of course, like the name suggests, is a real or imaginary surface that pretty much borders the system and separates it from the surrounding. And note that boundaries can either be fixed or moving, and mathematically speaking, they have 0 thickness and 0 mass. And now a more particular type of system can be a closed system, which in this case is a system that contains fixed mass, and in it no mass can cross the boundary of the system. So particularly the mass remains constant. And so the key things to remember about closed systems are that mass cannot enter or leave the system, but however, energy can still cross the boundary. And that is energy in the form of either heat or work. So energy can cross, but not mass. And now additionally, another type of system is an isolated system, which is a bit of a more theoretical or abstract type of system, where both energy and mass cannot cross the boundary. And so one example which may come to mind could very well be the universe in its entirety, since it is said that there is nothing more outside of it to interact with. And now, last but not least, we have an open system, also known as a control volume, and it is defined as a properly selected region in space, again for study. But unlike a closed system, here particularly both mass and energy can cross the boundary. And now this particular system is the most commonly used in engineering thermodynamics, with some examples being compressors, turbines, and nozzles. So for example, let's say we have this nozzle here, which I'll label as a control volume. Of course, here it's going to have a boundary around the border of the control volume. And typically we'll have mass entering the larger side of the nozzle on the left, crossing the boundary, going through the nozzle, and exiting at the smaller side of the nozzle on the right. And notice that this system includes both a real boundary, which are the actual physical walls of the nozzle, and imaginary boundaries, which are at the inlet and outlet, where the mass is going in and out of. And so from this particular configuration, you can see that you can have both real and imaginary boundaries in your system, and you have some form of mass and energy going in and out of the system. And keep in mind that this type of system is again the most commonly seen in thermodynamics, since it is also the most natural and commonly seen type of system in real life.